So hello everyone, welcome to this new video. So in our previous video we have started with the resonance chapter 2 of module 5, and the module 5 first chapter, that is two-port networks, we have already covered it. Those who have not seen it, please watch it, and hope that all the backlog students have tried to clear the backlogs, because I have provided only 2.5 modules, and all the 2.5 modules easily easily you could score because detailed explanation was provided. So now from here onwards I am making the videos for all the third sem students, because upcoming exam of network analysis is for third sem students, right? So please circulate this. I know that the most of my audiences are of 5th sem, so please circulate it to your juniors and say that we are having this channel called VTU Academy and we have started with this network analysis. Hope it would be useful for them. And also we have started with the resonance chapter here, and we have discussed few concepts, that is series resonance, Q factor, and the different kinds of expressions. So please, those who have not seen my previous video, please watch it. So let's continue with the previous session only. The one more concept is related to voltage across the inductance and capacitance under the condition of resonance. What is the voltage across L and C under the resonance condition? Let us see what the value of voltages we are going to get. Okay, very simple. Under resonance, the current in the circuit is maximum value, and it is given by I naught, that is at resonance I is represented as I equal to I naught. Okay, you know that at resonance I equal to I naught. We know that the simple expression of I is equal to V by R according to Ohm's law. That only I have written it here. That is I naught, that I have written it as V by R. So now under resonance, voltage across the resistor RL or the load resistance is given as VL. VL is equal to I naught into J times XL. Okay, where this XL is the inductive reactance. Okay, so this is the expression for VL under resonance, voltage across the resistor RL. It is given as VL is equal to I naught into J times XL, and VL is equal to the value of I naught. I have just written it here, V by R. So substitute that, V by R into J times, what is XL? XL is equal to omega naught L, right? Where XL is the inductive reactance, omega naught is the series resonating frequency, and L is the inductance. Okay, so that I have substituted here. So VL I am getting it as J into omega naught L divided by R into V. I have just replace some of the terms. I have written it as J into omega naught L by R. Why I have grouped it? Because we can say that omega naught L by R is equal to Q naught. That is the quality factor which I have discussed in the previous session, right? Well, the formula for quality factor is Q naught is equal to omega naught L by R. So that only I have replaced it here. So that is our final value of VL, that is the inductive voltage. What we will be getting, that is equal to J into Q naught times V, where Q naught is equal to omega naught L by R, and this Q naught is the quality factor. Okay, so that's why our expression VL is equal to Q naught times V, 90 degree volts. Why it is 90 degree? I have just replaced this complex term by 90 degree. Okay, so that's why VL we would be getting it as Q naught V 90 degree volts. This 90 degree you should not, it's better that you not consider it, because this would be our general expression for VL. So in order to represent it in order to eliminate this complex term, I have just written this 90 degree volts. Okay, yeah. So this is the value of VL. Now voltage across RL is done. Similarly, let us try to find the voltage across RC, that is the capacitive resistance. Okay, what we would be getting, VC is equal to I naught times, now it is minus JXC. Okay, because in the expression we have J into XL minus XC, right, in place of reactive part. So that's why now here we have JXL is done. Now if we multiply, we would be getting minus JXC, right? So that's why we would be getting VC is equal to I naught times minus JXC. So VC is equal to I naught is equal to V by R minus J, and the value of XC, that is the capacitive reactance, is equal to 1 by omega naught C. So substitute that, what we would be getting. So now bring this J in one side and write 1 by omega naught CR times V. Again we know that what is the formula for quality factor, Q, in terms of capacitive reactance, that is equal to 1 by omega naught C times R. Right, so that only I have replaced here. So VC, what we would be getting, that we would be getting equal to minus J into Q naught times V, and this minus J now it is replaced by minus 90 degree angle. Okay, so VC is equal to Q naught times V with the negative phase shift of 90 degree, and VL is equal to Q naught times V with the positive phase shift of 90 degree. So please keep it in mind, these expressions, that is voltage across inductance and capacitance under the resonance condition. So keep it in mind. So these are the expressions obtained. So from the above expressions, it is clear that at resonance the magnitude of VL and VC are same, but they are out of phase, hence both cancel each other. But VL and VC are Q naught times the applied voltage, that is VL is equal to Q naught times V and VC is equal to Q naught times V. And you know that due to resonance the angles would be getting cancelled out, since resonance condition we know that Z is equal to R, and we are having plus J into XL minus XC, and here XL minus XC would be getting cancelled out because of the 90 degree positive and negative phase shift here, so that would be inversely proportional and they would be cancelling each other. So we would be left with Z equal to R under resonating condition. This is the expression we get. Okay, but VL and VC are Q naught times the applied voltage. You can see here VL and VC are Q naught times V here in both the cases, right? Q naught is a number always greater than unity. Okay, this Q naught is always strictly greater than unity. Okay, you should be keeping that in mind. Thus, under resonance, voltage across L and C are greater than the applied voltage V. So therefore, under resonance, we can conclude that by saying that under resonance, series resonant circuit acts as a voltage amplifier, where Q naught is the amplification factor. Okay, the series resonating circuit under resonance acts as a voltage amplifier because it is completely controlled through voltage by having the same values of inductive and capacitive voltages, that is Q naught times V. Okay, and this Q naught in this series resonant circuit is represented as the amplification factor. So this was one topic related to voltage across series and under resonance, voltage across inductance and capacitance. Hope this is clear. So now let us discuss one more topic, that is bandwidth and selectivity. Okay, what is bandwidth? What is selectivity? Let us discuss. First, let us get with the definition of bandwidth. Bandwidth is not a new term for you guys. You have already heard it before. Okay, it is just the differences between the cutoff frequencies. Okay, yeah. Cutoff frequency means from lower frequency to higher frequency, and we would be having one constant frequency. Then from that we would be getting from higher frequency to lower frequency. That region where the frequency gets changed, that region is called as bandwidth. Okay, in brief, those who don't know. So according to the network analysis, now what is bandwidth here? Bandwidth is the bandwidth of a series LCR circuit is defined as the band of frequencies over which the power in the circuit is half of its maximum value. Okay, so here it is defined in terms of power. That is, the power in the circuit is half of its maximum value. So let us try to write this expression mathematically. That is, at frequency resonance, current is maximum. So we know that I naught is equal to V by R. Impedance is minimum. Current is maximum. Okay? Yeah. Hence, power is maximum and it is given as P naught. In resonance, again P naught, or that is equal to maximum power. So P max is equal to I naught times square into R. Since we know that power, in order to represent in terms of current, it is represented as I square R. If you want to represent in voltage, it is represented as V square by R. Okay, these expressions you know, that is P naught would be equal to I naught square into R. Now half of the maximum power is given as, since according to the bandwidth definition we know that power in the circuit is half of its maximum value. So we should be dividing it by 2, that is P max by 2 or P naught by 2. So initially let us represent it as a P dash is equal to P naught by 2, that is I naught square R by 2. Again what I am doing is I naught square by 2, I am writing it as I naught by root 2 the whole square. Why? Because if we multiply this, what we will be getting? I naught square divided by root 2 the whole square, that is equal to 2. So that's why I have replaced this I naught square by 2 with I naught by root 2 the whole square into R. So this is the expression we get for bandwidth in terms of power, that is half of its maximum power, that is P max or P dash, that is equal to P max by 2, and also we can write it as I naught divided by root 2 the whole square by R. So at frequencies where power in the circuit is half of its maximum value, the current becomes 1 by root 2 times, that is 1 by root 2, we can see it here, 1 by root 2 times or 0.707 times of its maximum value. The frequencies at which the power in circuit is half of its maximum value is called as half power frequencies. Okay, the half of its maximum value, the frequencies are called as half power frequencies. Also, they are given with two of the different names. One is higher cutoff and lower cutoff frequencies. So I hope this expression is clear. So this is the graph here, plot current versus frequency, as I've told you. So here the frequency is getting increased, and for some time it would be staying constant and it would be getting decreased, and that region of the increase and decrease, that is called as bandwidth. Okay, so here I have represented it. Here we have written one I naught here, I naught by root 2 plot, and this is the I naught plot here, and here I naught by root 2 plot is named it as F1 frequency, and here where the frequency is getting decreased, that is called as F2 frequency, and this bandwidth is given by a higher cutoff frequency and by lower cutoff frequency, that is F2 minus F1, and this is the resonating frequency F0. Okay, so here I have divided it by delta F and delta F. So hope this is clear. The bandwidth expression is F2 minus F1. At resonant frequency, power is given by P0 is equal to P max, that is I naught square by R. At frequency F1, P dash is half times I naught square R. Okay, half times I naught square R for at frequency F1. At frequency F2, P dash is equal to again half times I naught square R, where F1 and F2 are called as lower half power frequency and upper half power frequency. Bandwidth is represented in terms of F2 minus F1 and its unit is hertz. So therefore what we can conclude that the half power frequencies are also referred as the 3 dB or the 3 dB frequencies, because the power at the frequencies is 3 dB less than that of the resonance. Okay, so this is the conclusion, we can note it here by these things. So this was the plot for which I've just proved the definition of bandwidth, okay, by plotting the current values for I naught, and one is for I naught by root 2 according to the half power frequency condition. Okay, yeah. So this was the brief explanation of bandwidth part. So we are having one simple derivation, very lengthy, but it's very simple, that I'm going to explain it in the next session. So that's all for this session, guys. In this session I've covered with the expressions for voltage for across L and C in resonance, and I've discussed with the bandwidth. Okay, so hope this session is clear to you all. Let us see you in the next session. Please like this video, share this playlist to a huge number. Thank you.